I have been working on a physically based renderer for my game engine. To demonstrate the result, I have been working with Naevrah. She's an artist and friend of mine, and she created this really cool 3D model. If you want to check out on what else she's working on, I'm going to put links to her artworks in the description. There are a lot of steps involved to render this 3D model, and I'm going to walk you through the major ones. After walking you through the shader code, I'm going to show you how the different textures involved affect this 3D model. All the color and light calculations are done in the fragment shader. This is where the reflectance equation is used to compute the color of every pixel. The reflectance equation is composed of 3 parts. The first part is the bidirectional reflectance distribution function, or BRDF. It influences how the surface interacts with incoming light. The second part is the incoming radiance of, in this case, one directional light source. And the last part adjusts the light intensity depending on which angle the light hits the surface. The BRDF is also composed of 3 parts: the Fresnel function, geometry function, and normal distribution function. As a Fresnel function, I use the Schlick approximation. When I remove the other 2 functions from the BRDF, we can see the effect of the Fresnel function. We can see that the surface becomes more reflective at glancing angles. This is often called the Fresnel effect. The Fresnel function takes one parameter f0. It describes the specular color of the surface when the light is perpendicular to it. For example, water has a f0 value of 0.02, while f0 for iron is around 0.56. The electrics like water have very low f0 values and are uniform across RGB channels. Because of this, the electrics usually use a constant f0 parameter since they don't vary as much. Metals like iron have much higher values, mostly above 0.5. Additionally, they often have different values in different color channels. Gold, for example, has a red channel of 1 but a blue channel of only 0.34. So instead of using a constant, metals usually use the albedo color as f0 parameter. The geometry function and normal distribution function are based on microfacet theory. In a microfacet model, every surface isn't perfectly flat, but instead there are many tiny facets pointing in various directions. The rougher a surface is, the more light is spread in different directions. The geometry function and normal distribution function aim to describe this behavior. The normal distribution function, or NDF, gives a statistical distribution of which direction the microfacets are facing. I'm using the GGX distribution for this. The geometry function describes how much light is blocked or shadowed by other microfacets. I'm using the Smith masking shadowing function to calculate this. The lambda function of the geometry function depends on which NDF is chosen. Fresnel, NDF, and geometry function make up the specular color of the surface. This is the light that gets immediately reflected at the surface. Light entering a surface gets either absorbed or refracted, meaning it enters the surface, bounces around in it, and then exits the surface somewhere else. This is also called subsurface scattering or diffuse reflectance. Luckily, the math here is not as complicated as for the specular term. Noteworthy is that we use the result of the Fresnel function to determine how much light has already been reflected and is consequently not available to refract under the surface. Additionally, metals reflect all light at the surface and have no subsurface scattering. All light entering a metal gets absorbed by the material. The ambient color simulates the idea that light bounces around the environment before it hits the surface. This leads to the result that light comes from all directions and no part of the surface is just black. There are several textures that influence the appearance of a surface. The albedo texture describes the color of the surface. A low subsurface albedo means that a lot of the incoming light is absorbed by the surface, leading to a darker visual appearance. The roughness texture describes how the microfacets of the surface are oriented. Lower values mean the microfacet normals are more aligned to the surface normal, leading to sharper reflections. Higher values mean the microfacets point in various different directions, leading to distorted reflections to a point where they become unrecognizable. The ambient occlusion texture gives information about how the ambient light is interacting with the surface. In real-time applications like games, they are often pre-computed to save performance. The metallic texture describes if a surface is metallic or dielectric. Since metals absorb all entering light, there is no diffuse color. For metals, the albedo texture is used as F0 parameter for the Fresnel function. The normal texture or normal map provides information about the direction of the surface normal. In contrast to the roughness texture, the normal map stores concrete directions. The roughness texture deals with subpixel microsurfaces and describes their orientation relative to the one stored in the normal map. Let's take a look now at how the different textures affect the appearance of the 3D model. This is how it looks without any textures. It appears smooth because the vertex normals aren't perpendicular to the surface. Instead, they are averaged with other normals of connecting faces. The albedo texture brings the base color to the model. When I add the metallic texture, you can see the difference in the blood and dagger. They get darker since the diffuse part of the light calculation becomes 0. When I add the roughness texture, we get some specular reflections on the stones and a strong reflection on the dagger. Adding the normal texture adds a lot of detail to the model. For example, the cracks in the stones become much more apparent. And since the blood isn't flat anymore, there are some specular reflections on the edges. Adding the ambient occlusion texture makes the areas darker that are harder to reach by the light. Implementing this has been a very fun but also challenging experience. I'm really glad I could work together with Naevrah to test the engine with a custom-made model. This makes the process and end results so much more rewarding to me. Let me know if you liked this type of video or if you have any kind of feedback. Until then, thank you for watching and see you next time.